So I'm Mattia Walschaers. I'm a CNRS researcher at the Laboratoire Kastler Brossel in Paris. So you can actually even see the lab on the picture. So it's here in this tower here, or well, we're not in the tower as always. The administration gets the nice offices and we are kind of around somewhere. So for now, as I'm a theoretician in the lab, I'm mainly working from home. As far as I understood, you got a talk by Nicolas Treps I guess already a few weeks ago on multimode non-Gaussian states, where he mainly talked about the experimental side. And I now want to give you kind of the complementary theory perspective. So I work in the same group as Nicolas, and I am basically kind of in charge of the theory developments in our group. So to kind of dive right in. So we work on continuous variable systems, the continuous variable approach to quantum optics. I assume that all of you have more or less heard of this. If you're not very familiar with this, you can think of continuous variable systems basically as, so you have light, and the continuous variables are going to be the electromagnetic fields themselves, mainly like the field quadratures that we use as observables that we measure. If this is kind of not very familiar, you can think of the electromagnetic field and its modes as a bunch of quantum harmonic oscillators. And so the field quadratures are going to behave in the same way as the position and momentum observables of these quantum harmonic oscillators. And so in these optical modes, in this continuous variable approach, what we really like is the fact that we can generally create very large entangled states. So here I give you an example from the group of Akira Furuzawa. So they use this kind of temporal multiplexing to have their optical modes being time bins, and they can use this multiplexing scheme to create very large entangled states, where here in this representation, so this is a graph state, so every little node represents an optical mode, and all the connections represent entanglement links. So you get these very large entangled states. Other groups make them as well, typically with slightly different setups. But so that's kind of the thing that we really like about continuous variable systems. But these big entangled states, they have a disadvantage in the sense that they are completely Gaussian. So if you would do any kind of measurement of these quadrature operators, you would always just get Gaussian measurement results, and this can be easily simulated. So on its own, these states are not sufficient if you want to do a quantum information protocol and get a quantum advantage. So the additional element that you need is Wigner negativity. So there are several papers, I just cited one of them, that basically show that if you do not have Wigner negativity at some point in your system, this could be in the measurement, this could be in some, let's say, in some gates that you apply or in the initial state, then you can simulate the whole thing on a classical computer. And so here you see, like, this is the one mode example of a Wigner function, and you see like the Wigner negativity appears here in this little bump. So this is the kind of thing we want. And so in our group, what we are working on is trying to put these two sides together. So to see how can we create these reasonably big entangled states. The ones that we create are more around between 10 and 20 modes. So it's much more modest, let's say, in size, but still you have a reasonably sizable entangled system, and we try to induce this Wigner negativity in these states. So how do we do this? How do we create Wigner negativity? Well, there are basically two main schools of thought. So one is the one that applies deterministic methods. So there are many examples, but the one that I find kind of the easiest to explain is this one, where you have these quantum dot single photon sources, and they really work as, well, they're quite complicated to produce. I don't understand the inner, let's say, solid state physics in detail, but the idea is that you push a button and a photon flies out. So you really get on-demand single photons. Single photons have a negative Wigner function, so you could say that you're on-demand generating Wigner negativity. Then what is generally more popular in optics still are these probabilistic methods, where again, you could look at one of the typical methods to actually create single photon Fock states is to pump a nonlinear crystal. You create a very weak two-mode squeezed vacuum. And well, this will basically mean that you have vacuum most of the time. Every now and then there is a pair of photons created, one photon in every mode. And so if you detect a photon in one mode, you herald the presence of a photon in the other mode. So this is a probabilistic way of creating, again, a state with a negative Wigner function. But then you have, let's say, other setups that apply similar ideas. So in this example, they create here with this OPA a single mode squeezed vacuum. They send it through a highly transmitting beam splitter. So virtually all of the light is going to be transmitted. And just a very small fraction is taken out. This goes to a photon detector. And when you detect a photon there, you know that exactly at that time, there is a photon missing in the other arm. And so this allows you to create these photon subtracted states, which still have some properties of the initial squeezed vacuum. So you still see the squeezing and so on. But now, because you have this photon that is missing, you basically created this additional Wigner negativity on your state. And so what we do in our lab is basically the same thing, but we do this for multimode light. So this would be basically for a single quantum harmonic oscillator if you want. And what we do is we have a large group of quantum harmonic oscillators, possibly entangled and so on, that we send into this kind of photon subtractor, and we want to be able to subtract a photon in any mode we like. And so when you talk about harmonic oscillators, any superposition of harmonic oscillators is again a harmonic oscillator. So what we really say when we want to do something mode selective is that we want to take our modes, our optical modes, be able to take any superposition of them and say we apply an annihilation operator in this mode. So I'm not going to spend too much time explaining the experimental details, but I do want to focus in my talk specifically on these probabilistic methods. So my outline is the following. I will first present you a kind of general phase space formalism, phase space description, phase space description for these kind of conditional operations in general. Then I will explain you how we can use this general formalism to model photon subtraction. And then at the end, basically also because you asked me before, because this was something that you found interesting, I will give a kind of a hybrid theory experimental part on how we characterize these states and how we basically, how we can deal with big multimode non-Gaussian states and still kind of extract some properties of them in experiments. And then at the end, of course, there will also be a little outlook with some take-home message and so on. So first things first, so when you do conditional state preparation, I'm a theorist. I think most of you maybe are also theorists. So to me, at least, a quantum optics experiment of this type is always taking the same form. So I assume that I have some source that produces a state. This can be highly multimode. I don't really care whether I have spatial modes or time frequency modes or whatever. The only thing that is important is that you can split basically your set of modes in two groups. So you create this bipartition where I call one group G and the other group F. And I suppose that the state that I'm producing with this source is somehow something that is convenient to produce in an experiment. So typically this will be a big Gaussian state, so that I just call rho here. And I assume that there is some correlation between the modes G and the modes F. This doesn't have to be a quantum correlation a priori, but there has to be some correlation. Otherwise, the whole scheme that I'm describing would be really boring. So then the next thing I'm going to do is I'm going to apply some kind of operator on the modes G. So in general, you can think of a measurement where you are going to condition on a specific measurement outcome. So you could say that this is a kind of a POVM element that you apply to the modes G. And then the question is, when we do this, what is going to be the state or the properties of the state that we herald in the modes F. Now, in general, I can formally write down what this conditional state is. I can just take my my POVM element, let it act on the state rho, and then trace out the modes G here. So when I do this, this is the thing that pops up. Then, of course, this will not be a well-defined state, and I have to renormalize with the success probability. So this would be the trace over the full system, and this this trace here basically just describes the probability that you actually get the measurement outcome upon which you are conditioning. Of course, this is kind of a nice and formal result, but it doesn't really say as much, for example, about the Wigner function. So the question I want to ask now is, when I do this kind of general scheme, when will I get Wigner negativity on the side here of these modes F in this conditional state? So this means that I have to understand Wigner functions, and so I'm going to translate everything in this setup to phase space, so associate the Wigner function with everything. So basically my global state, I'm going to describe it by W, which will be a Wigner function on the full phase space of F and G. In general, it will be a Gaussian. Then I associate a Wigner function with this POVM element that I'm applying. So if you would do a projective measurement, this would just be the Wigner function of the state on which you're projecting. And this is, of course, going to be a Wigner function that's only defined on the phase space variables associated with the modes G. And then I have on the other side this conditional Wigner function on the modes F that I'm actually interested in. So I can basically translate this density matrix identity that I had on the previous slide to phase space by just replacing every operator with its respective Wigner function and replacing the traces with integrals. So the trace over the modes G will become an integral over the phase space associated with G, and the trace over the full system will become an integral over the full phase space. And so again, I mean, still formally we don't really learn too much, but we can use a funny trick. So I'm going to use the fact that actually this global Wigner function here is positive and is normalized, which means that it actually has the properties of a probability distribution. And so I can formally define a conditional probability distribution on the modes G, conditioned on some value of the modes in the modes F. And so, but this is the formal definition. So the WF that appears here would be the reduced state for the modes F that is produced by the source. So basically you take the global Wigner function, you trace out or you integrate out the modes associated with G. And so what is left here for the modes F, this would be the WF. So I'm just going to use this identity and inject it back into this definition of the conditional Wigner function. And what you see is that you have this WF here, this reduced state pops out. So this just factors out, and I have this new integral that appears, which has this conditional probability distribution in it. So I'm going to give this a name. So I call this the conditional expectation value of A. At the bottom, we still have the actual expectation value of A. And so you could think of this, because A is a POVM element in general, you could think of this as a probability to get the outcome A. This is somewhat like a conditional probability. And so this whole phrase here, basically, or this whole expression is kind of like a Wigner function version of the Bayes theorem. And so I'm saying Wigner function version because actually this conditional expectation value here, it's not really going to be a conditional probability because for example, it can reach negative values and so on. So it is really the Wigner function version of Bayes theorem in the sense that you have to deal with all the complexities that go with working with quasi-probability distributions. So what is quite cool now is that when we look again at this expression, so now I put it here, of this conditional Wigner function, is that, well, we have this reduced state appearing here, which is just going to be a Gaussian if the initial state is Gaussian. Then we have this, this probability of getting the outcome A, which is just a number. And then I have here actually this conditional probability, which is itself, because of the value we are conditioning on, a function of the phase space variables in F. And this is going to contain now all of the non-Gaussian features in my state. And so in particular, I'm quite interested in understanding when this quantity becomes negative. And so, of course, this conditional probability distribution that appears here, it is a well-defined probability distribution. So it's always going to be positive, which means, well, if I want to get some values of xf for which this quantity becomes negative, I need to have Wigner negativity in the POVM element. Otherwise, you will never get Wigner negativity in the conditional state. So this is kind of straightforward, maybe, but what is interesting is that this alone is not enough. Actually, whether or not you get Wigner negativity here in your conditional state or in this conditional expectation value will also depend a lot on the properties of this conditional probability distribution that we have here. So let's explore what this object is. And now I'm really going to explicitly assume that my initial state that is produced here is a Gaussian state. And if this is the case, then this conditional probability distribution is also going to be Gaussian with a displacement that depends on the value that I'm conditioning on. So this is classical probability theory, basically. And the covariance matrix, which will just be given by this Shor complement. So first thing to note is that it actually does not depend on the value upon which I condition. And then, so just to give you kind of an idea of what all the notation means. So VG is the covariance matrix that describes basically all the variances and the correlations between the different quadrature operators in the modes G. So for the reduced state, basically just to these modes. VF is the same thing for the side F. Then you have VGF, which contains all the correlations between the quadrature operators in the modes G and the quadrature operators in the modes F. So this is the object that kind of describes the correlations between the modes on the two sides. And so this Shor complement is quite fundamental in mathematics. It has some interesting properties, but why we like it here is because it also has a very fundamental connection to quantum steering. So first of all, the thing to note is that this is a well-defined covariance matrix of a probability distribution in the sense that it's always going to be a positive semi-definite matrix, but at the same time it does not necessarily satisfy the Heisenberg uncertainty relation. And this means, so if it does not satisfy Heisenberg uncertainty relation, well, in that case, this conditional probability distribution is not a well-defined Wigner function of a quantum state. So, and it turns out that if it violates this Heisenberg uncertainty relation, that you can do quantum steering from the modes F to the modes G with Gaussian measurements. So Gaussian measurements on the side F will be able to steer Gaussian measurements on the side G, basically. And then, so I call this Einstein-Podolsky-Rosen steering when I talk about quantum steering with Gaussian measurements. And the interesting thing is that the inverse statement is also true. So if I have this EPR steering, I will also find that this covariance matrix or this Shor complement violates the Heisenberg uncertainty relation. So you find more details in these papers. I kind of assume that you all have a bit of an idea of what steering is. If not, after the talk, I can explain you a little bit more in detail. I suppose probably some people among you know it better than I do, but so let me just carry on, because this equivalence, let's say, is important in the sense, oops, wrong direction, in the sense that I can invert it. So I can suppose that there is no EPR steering. And this means that, well, that this Shor complement actually satisfies the Heisenberg uncertainty relation. This in turn means that this conditional probability distribution actually describes a well-defined quantum state for every possible value of xf, which I can call rho g. And so as a consequence, when I then look again at this conditional expectation value of A, well, actually this turns out to be the trace of rho g with respect, or multiplied with this POVM element. And because this A is a positive semi-definite operator on the Hilbert space, this expectation value here is always going to be positive, regardless of the value xf that we condition upon. So a long story short, if we do not have this EPR steering, or steering with Gaussian measurements from modes F to modes G, we will not get Wigner negativity in this conditional state. And this is a quite strong statement in the sense that it doesn't rely on which measurement I'm doing on this side. It just says, if you cannot do Gaussian steering from modes F to modes G, you can do whatever you want on the side G, you will never get Wigner negativity on the side F. Okay, so this also has some quite strong constraints on what you can actually do with this Wigner negativity. So here, I now suppose that I explicitly have like one mode here. So G is now going to be one mode. And then I'm going to take not one mode in F, but multiple modes. So let's say that we have 3 now. And now I'm going to use the fact that there is something called read monogamy. So this means that if, for example, this mode F1 can already steer mode G, it automatically implies that modes F2 and F3 cannot do this. So here again, I'm assuming that my states, everything is Gaussian. And so I cannot do Gaussian steering from mode F1 to mode G and from mode F2 to mode G. So at most, one of these modes can steer at the same time. And this has an important consequence, because we need the steering to basically tell us where we can make Wigner negativity. And so when we then define the negativity volume, so basically you take the Wigner function of this, or this conditional states Wigner function, you take the absolute value and you integrate it over its phase space. This will, if you have Wigner negativity, give you a value larger than 1. And if you subtract 1, you get basically the volume of this function that is negative. So this negativity volume then can be combined with this read monogamy that I described on the previous slide to actually derive a monogamy relation of the Wigner negativity that we create in this way. So here on the left side of this inequality, I show you the negativity volume of the entire Wigner function here. So for the 3 modes jointly. And this is always going to be larger than the sum of the individual Wigner negativity volumes. And of course, due to this read monogamy, we know that basically at most one of these can be non-zero at the time. And on top, it will always be smaller than the global Wigner negativity. So this is kind of the very quick sketch of how you prove this. But then the funny thing is that you can, of course, also have cases where you do not have any local Wigner negativity, but you still have global Wigner negativity. So this is, there is always this kind of story between what is happening locally and what we can see locally in single modes and what is happening in the global state. And this is one of the complexities of going multimode, is that not everything which kind of globally happens can just be kind of compressed somewhere into one mode. Okay, so to kind of wrap up this first part of the talk, what I showed you is that this Gaussian quantum steering from modes F to modes G is a necessary resource if we want to create Wigner negativity in modes F by doing some kind of by conditioning on some operation in modes G. So you find this in this paper, and then we also have the opposite statement, which is true, or it's also a sufficient resource in the sense that when you have this Gaussian steering, that you can always find some operation to do on the modes G that will give you Wigner negativity. This operation, or I think there are probably many more operations that will always work, but the one that we found was when you first do some local Gaussian transformation, so you may have to change the squeezing and maybe change the mode basis a little bit, and then you do a well-chosen photon subtraction here that will basically give you Wigner negativity on the other side. So in this sense, it's also a sufficient condition. And so this also gives me a nice transition to the next part, because clearly this photon subtraction is an interesting operation. So I now want to use this formalism that I described to model photon subtraction. So as I told you before, this is what we do in experiments. The idea is quite simple. We want to take our global multimode state, so let's say our ensemble of many quantum harmonic oscillators, possibly entangled or correlated to one another. And then I want to apply a well-chosen annihilation operator to this system. So basically, the idea is that, as I said, you want to be able to really, if you take an annihilation operator in every local harmonic oscillator, and you take a superposition of these annihilation operators, this will again be a well-defined annihilation operator. And so it's kind of these type of superpositions that we want to be able to choose freely. And so this, we have a whole nonlinear optics setup that allows us to do that in the experiment. So how do we model this? Well, you can always kind of, there are many different ways of deriving this model, but it always kind of boils back down to something like this, where you take your initial state defined in the modes F, you send it through some big interferometer, and the important thing, and the only thing that I care about in this interferometer, is that one of the output modes here, which I call B, is going to exactly be the mode is going to exactly be the mode in which I will subtract the photon. So the subtraction of the photon is then going to happen with a very highly transmitting beam splitter. So I'm going to take the limit at the end where the reflectivity goes to 0. And so effectively what I'm doing is I'm adding an initial mode which is in vacuum, and I'm coupling this auxiliary mode to my global state, taking out a little bit of light in this mode G, and I put here a detector. So then we're not finished. We still have to basically undo this initial basis change. So this is just the reverse interferometer that gets you back to your initial mode basis F. And then what we have here at the end will be the photon subtracted state in the modes F. So now the question is, how do we get the Wigner function of this state? Well, we can realize that this is actually exactly a realization of the model that I described before, where the outgoing mode G here is now this G that is produced by the source, and the outgoing modes F here, they will be exactly the modes that are the ones in my conditional state. So the ones that I'm actually interested in finding the Wigner function for. And so what remains to be done is to understand kind of what Gaussian state is produced now by the source. And this would be the state that you get when you take this initial state for the modes F, and you add also this auxiliary mode, which is initially in vacuum. Then you apply all these interferometers, this linear optics, and you get the state that goes out here in these modes F, and the state that goes out in G. So this is what we need. Once we have this, we can inject it into this general, let's say, Wigner function base theorem, and that's it. So the only thing that we really need to know now is the covariance matrix. So here I take the VF is a covariance matrix of my initial state here, that describes the state that comes in. Then I have the one here, which is a covariance matrix of the vacuum in this one mode that I couple in. And then I have this OBS, which just describes all of these interferometers. So let me just put that aside. So now I can use this covariance matrix to calculate the relevant Schur complement and so on. And I can insert all of this in this expression. So this W of A here will, of course, now, because I'm conditioning on a single photon Fock state, this will be the Wigner function of a single photon. The L prime counts the number of modes in G. So generally, this will just be one mode. So this is just going to be one. And so this conditional probability distribution, I can extract it from this, this covariance matrix. And then the last thing, which is important, is that when I get this expression for a general beam splitter here, I'm going to take the limit then at the end where this transmittivity goes to 1 or the reflectivity goes to 0. So this is this theta going to 0 limit. So I'm not going to go through the whole calculation. The result that you get ultimately looks like this. Let me just kind of quickly break it down. So you have these psi's that I introduced, which are basically all the displacements that you could have in your initial modes. They are kind of the mean field of the state. The VF is a covariance matrix of the initial state here. The VB is going to be like the reduced covariance matrix specifically that describes what is happening in this mode B here. And then I have this matrix B that pops up, which is kind of like a rectangular matrix that projects my 2m dimensional covariance matrix. So m is the number of modes. So in this case, this would be 4. And it projects this covariance matrix basically to the mode B, so to a 2x2 matrix. Okay, and so then finally, kind of a cute thing is that you have this W of F popping up here. So this comes from this general equation here. And you would expect that this is the Wigner function here that you have at the output. But because we take the limits where this beam splitter is highly transmitting, it turns out that if you do all the calculations, that this will also just be the Wigner function that you have for these initial modes. Okay, so this is the Wigner function that we obtain. And so you can, looks a bit complicated. You can ask the question, well, what can we now learn from this? Well, first of all, we have here this big modulus squared. And the modulus squared has one very nice property, which is that it's always positive. So all the Wigner negativity in this term is going to come from this, let's say, polynomial type expression here in front. And I have something here which is always positive. It turns out that you can always find the value of a point in phase space where this modulus squared is actually going to be 0. So it turns out that ultimately you will have Wigner negativity if and only if this trace here is negative. And I can just kind of retranslate this to saying that the trace of this this matrix here has to always be larger than 2 if I want to have Wigner negativity. So this is a simple condition. It's also a cool condition in the sense that it's, when we go back to this kind of general conditional operations framework, this condition is directly related to this Schur complement. So if I take the Schur complement in this limit where this little beam splitter that does the photon subtraction becomes highly transmitting, my Schur complement is approximately given in this way. And you see that basically when this condition is satisfied, this Schur complement will start to violate the Heisenberg uncertainty relation. So in this sense, it's kind of consistent with this idea that we need steering to get Wigner negativity. One observation that honestly, I think no one of us really understands whether this is just a coincidence or not, but this quantity here is very closely related to the quantum Fisher information for the global Gaussian state when you then do measurements in the mode B. So again, this, of course, so what this statement says is that you need some kind of a metrological quantum advantage in the mode B if you want to get Wigner negativity. At the same time, for Gaussian states, this kind of metrological quantum advantage basically just means that you need squeezing and non-classicality. So maybe this is just a coincidence. Maybe there is something more deeply connected to Fisher information and metrology there, and this for the moment we don't really know, but I always think it's kind of still cool to point out. And then finally, there is this monogamy relation that we kind of derived in general, and we get this now for free because this imposes quite some interesting constraints, because this tells us that Wigner negativity cannot just go anywhere when we subtract a photon. We cannot just get negative Wigner functions in a whole bunch of modes and so on. So I will come back to this in a bit more detail, because this really gives us quite some additional things to play with. So first I want to highlight a fun fact, which is that I can apply this kind of conditional state preparation framework on phase space also in a different sense. I can now assume that G is not going to be the auxiliary mode in which I'm like putting the photon detector, but I can assume that G is going to be the entire mode from which I subtract the photon. So basically I have my global state from which I'm subtracting a photon. I subtract a photon in one specific mode. I take out this one specific mode and I ask, what is the Wigner function going to be in all of the remaining modes? So all the modes in which I did not subtract the photon. And we can also describe this or answer this question with this framework. So again, we take this general Wigner function base theorem, and I now take A to be the number operator in this mode G here. So this comes from the fact that this photon subtraction is basically applying an annihilation operator. This is not a, let's say, a well-defined POVM element because it's not smaller than 1, but basically the whole framework that we derived still works. So it works in a very general sense of operations that you apply here. And so I can just do the calculation. And what I find is that the Wigner function for these modes, so the modes that are the ones that are orthogonal to the mode in which I subtract the photon, they have a Wigner function that is described in the following way. And again, what's interesting to note here is that you have this Shor complement popping up. And this will now be the Shor complement that describes the steering from the modes F to the mode G. So from the modes that are orthogonal to the mode where I subtract the photon to the mode from which a photon was subtracted. And if I have this steering, so if this trace is smaller than 2, I will always get Wigner negativity here on this side. And so this is quite cool because I can put all of these different things together in a little example. So to kind of go a bit down to earth, I always like to take a simple EPR state. You take 2 squeezed vacuum modes, you add maybe a little bit of noise to them, like thermal noise. You then add a phase shifter such that they're squeezed in orthogonal modes. And you mix them on a beam splitter. So if you did things well, there should be some entanglement here at the output. And I'm going to subtract the photon now in this mode B. And so now I can ask the question, well, globally, when will I have Wigner negativity? Well, you can take the covariance matrix of this 2-mode state that you produced, you invert it, and then you project this to the mode B. If this trace is larger than 2, well, you will have Wigner negativity globally in the joint Wigner function for the 2 modes. Then we have this additional condition that says that now if I take this global covariance matrix and I construct this Shor complement, and I see that basically the mode A can steer the mode B, well, in this case, I know specifically that there will be Wigner negativity to be found in the mode A. And then because we have monogamy, I don't even have to do any calculation. I know automatically that if I have Wigner negativity here in the mode A, because of this monogamy relation, I cannot have Wigner negativity in the mode B. At the same time, I could kind of close my eyes, forget about the existence of the mode A altogether, say that I just take the reduced state for mode B, take the inverse of the covariance matrix for the mode B, and if this trace here is larger than 2, I have my negativity condition now solely for the mode B. And in this case, I also get that there is Wigner negativity going to be here in this mode. And so one interesting thing that we kind of get for free from these monogamy relations is that these two conditions cannot jointly be true. If you find the Wigner negativity in one mode, it cannot be in any other mode that is orthogonal. So, okay. So this basically wraps up the whole idea of how do we theoretically describe these states. And now I want to take like 5-10 minutes more to tell you how we actually go about in experiments when we have big multimode non-Gaussian states, how we can still kind of understand stuff about them. So the first thing is, well, this is what our experiment looks like. I have initially here my source that produces the Gaussian states from which I'm going to subtract photons with the photon subtractor. And then finally, the point that I want to highlight here is the measurement stage. So I'm actually, as you see, we only have one homodyne detector, which means that we're only measuring one mode. But because we have this pulse shaper here, this basically allows us to tune any superposition of quantum harmonic oscillators to choose and to measure the quadrature that is associated with this specific mode. So when we do this, we get experimental data that look like this. So this is actual data. And what we can do with them is we can take an off-the-shelf maximum likelihood tomography protocol to reconstruct the Wigner function of this state. So this is very standard. I think most people in continuous variable quantum optics who work with non-Gaussian states all use this kind of approach. So we can tune this approach to measure in whichever mode we want, which allows us to do things like this. So here you have the modes in which we subtract a photon. Here we have the modes which we measure. And this is a specific mode basis. So these are actually uncorrelated modes, so uncorrelated harmonic oscillators. And so basically, if I subtract the photon here in HD0, I expect something to happen in HD0, and you see you get Wigner negativity, but then you do not see anything, or you don't see much happening in the other modes. This means that you have good mode selectivity in your photon subtraction. You can do this when you subtract the photon in the other modes, and basically what you see is that it works. And now I can apply this also to study the specific example that I explained. So I gave my modes a new name. So I have EPR0 and EPR1. I looked at the Gaussian state that we have. I just calculated the Shor complement from the experimental data. And what I found is that it is smaller than 2, just like very weakly smaller, but it is smaller. And so you get that like mode EPR0 can steer EPR1, and EPR1 can also steer EPR0. And as a consequence, we see indeed, as expected, that if I subtract the photon in EPR1, so this would be this plot, and I measure EPR0, I see that there is Wigner negativity. And when I measure EPR1, I see that there is no Wigner negativity. So this is, we have this monogamy in play, and we have this steering in play. And so we can test these, let's say, these local features. And so this tells us how we see local Wigner negativity. We can do this, of course, seeing something locally, you can do with just a single mode measurement. But now the question is like, of course, when we know that there is local Wigner negativity, there has to be global Wigner negativity. But there might be many cases where you don't have local Wigner negativity. So the question is, can you still see or do something to see global Wigner negativity in a kind of scalable way? Well, let's do a test. Let's do so here I show you the measurements for 10 modes that come out of this kind of homodyne detection scheme. And let me show you the measurements of 10 other modes for another state that come out of such a scheme. And now let me ask you, well, for which of these data do you expect there to be a Wigner negativity? So honestly, I don't see anything in this. Like when I look at this, I see clearly that, I mean, there are differences and so on, but to say, well, clearly the negativity has to be here, I have no idea. Well, I mean, I cannot see it from the data, but I do have an idea. I know that the Wigner negativity is actually on the left and not that there is no Wigner negativity on the right. And the only reason why I know this is because I simulated these data from a Wigner function that I know, and I know whether it's negative or not. So, I mean, we can play this game, look at these data, but I mean, generally we don't really find a pattern. But this doesn't mean that there isn't any pattern. So the very simple idea that we had was, well, we can simulate these traces for various states. Let's just do this for thousands of different states that we generate. And let's just basically feed all these data into a machine learning protocol and ask it to find us a pattern that tells us when there is Wigner negativity or not. And so these are the data that we got out. So this comes from this paper, and you see that actually for 3 and 5 modes, this works remarkably well. Like you have basically 95% certainty that you get the right basically the right result, that it correctly predicts whether or not you have Wigner negativity. For 10 modes, this seems to perform a bit less. We now know that this is because we were a bit stupid in the sense that we run the algorithm and we tuned it for 3 modes, and then we just use the same parameters in the algorithm for more modes. If you optimize a bit better, you can basically get all of these curves to be more or less around the 95% range. We only figured this out after we had already published the paper, so I prefer to basically show you the published data. But in principle, we can do a bit better, we think now, or we know now. Also, when you go to the limit where you have only few modes, this is a limit where you can still use maximum likelihood methods, which seem to perform a little bit better when you really have a lot of measurements. But if you only have a very small number of measurement results at your disposal, you see that our method really gives you a much better prediction of whether you have Wigner negativity or not. And what is, to me, completely remarkable of this approach is that we do not use correlations between data in different modes. So basically, you could measure each mode individually, one after the other. Like you measure a mode basis, you feed this into the algorithm, and it will tell you or predict whether there is Wigner negativity or not. So this is, let's say, it's not cryptography or anything. It's not a certification scheme, but it is a very good way to benchmark your experiments. And of course, so maybe to tell you what we did when we did these simulations, I simulate, of course, only states that I can actually simulate. So a lot of this is basically, we only looked at single photon added and single photon subtracted states. So this is a reasonably limited class. So maybe there is more exotic types of Wigner negativity that this algorithm would not recognize, which is exactly why we are now trying to kind of simulate data for other states and feeding them in to the same algorithm. And I'm still surprised that the thing seems to perform reasonably well. So I guess there will definitely be some follow-up work on this in the next few months or years. So I showed you that we can see global Wigner negativity. A lot of this talk has been about Wigner negativity. And so now, in the final few minutes, I want to kind of address the question whether we can actually see correlations and say something about correlations. And this becomes hard when you have many modes. So, but it still works. So what we did is the following. Here we show in this kind of imprinted structure a graph state. So this means that every vertex here, every little dot represents an optical mode, and every connection represents an entanglement gate, a CZ gate that you apply. So you get a big graph state in this kind of complex shape. And then we subtracted, well, actually up to 10 photons into this little vertex that I show you in red. So this is kind of the blueprint structure. This is the network that we make. And then interestingly, there are many networks or many structures that will emerge in this state. For example, when you look at correlations in the system, so here on this graph, what we show, or on this network, what we show is photon number correlation. So every connection between two modes tells us how strongly the number of photons in one is connected or correlated to the number of photons in the other. They're basically like to correlate. Okay, so it seems that my PowerPoint just crashed. I guess I will have to restart. So I will already kind of continue talking. So the thing that you see with these correlations is that basically there are 0 when the numbers of photons are not related at all. And then you have, when you have a 1, so this is a weighted network between 0 and 1, and you have a 1 when you have a perfect, like when number of photons in both both modes is exactly going to be the same. So if all goes well, you can again see my talk appearing. I was showing you this slide. You just have to put it back on. Yes. So this is the disadvantage of these pictures, which are quite heavy, to have them in good quality. So what you see here then is these photon number correlations, and basically this is the Gaussian state before photon subtraction, and then we look at the same network, but after we have subtracted photons. And what you see is that you have some structures which are reinforced. You have correlations which are increased. You also have correlations which appear, which were not there before. And so you see that this network changes. And a way to kind of more quantitatively see this is by generating many of these networks and looking at the histogram that we obtain. And we see then here, so this is the degree distribution. So it's kind of the sum of all the correlations that are connected to one mode, so the sum of all the links that are connected to one mode. And we see that this basically, this increases quite dramatically for some vertices after photon subtraction. And so basically this means that the correlation is generally enhanced. So we then kind of try to understand why this histogram got this specific shape. Let me go quite quickly through this. So we have resolved basically which parts of the histogram come from which kind of vertices in this imprinted structure. So kind of the 1 are the vertices that are connected to the point where we subtract the photon with a CZ gate. The 2 are the next to nearest neighbors. So the one that are 2 CZ gates away of the vertex where we subtract the photon, and so on. And you see that once you go sufficiently far, so once you are 3 or more CZ gates away, you basically get the same histogram as for the Gaussian case, and it's really only locally that you will strongly influence these correlations. And then we even found that at distance 1, so the nearest neighbors of the point where you subtract the photon, their histogram or their degree distribution has a specific structure, in the sense that even like you have some vertices where the correlation seems to be reduced, others where it seems to be strongly increased. And we could trace this back to actually whether nearest neighbors are connected with the CZ gate to other nearest neighbors, or whether they are just all on their own, and so on. So you can really start to understand the structure of your correlations in this system using these network type methods. And because all that we are looking at is correlations between pairs of modes, we could in principle extract this even for a large system by doing just a whole set of 2-mode tomography. So we take all the pairs of modes in our system and we do pair tomography for all these different modes, get all the reduced states. And this would in principle allow us to construct this kind of data for real. So my take-home message, so I'm done. So the first thing I've shown you is this general conditional operations framework on phase space, which really emphasizes the importance of Gaussian steering if we want to create Wigner negativity. Then we use this model to describe photon subtraction in a multimode system from a multimode Gaussian state. This also works to do more than one subtraction. All the calculations become more complicated, but you can use all the same machinery basically. What's kind of interesting is that most of the results that I presented were not actually originally derived with this model. This was a result that we obtained only later. And it turned out that it was very useful to reformulate all of the things that we have done. But so many things we did based on correlation functions and characteristic functions and so on. So there are many different ways of approaching these kind of systems and their Wigner functions. And then finally, I highlighted that these kind of network methods and machine learning methods are quite useful for understanding what is happening in large multimode systems. So as an outlook, the things that we are interested in for the future. So I think we have understood a lot about Wigner negativity, and the next step for me as a theorist that I want to attack is entanglement steering, quantum correlations in general, and understanding how these non-Gaussian conditional operations actually change the entanglement properties of our system, maybe even create entanglement, create steering, and so on. So we have a very first step out on this where we look at entanglement increase due to photon subtraction in this recent paper here. Another follow-up project would be to understand in these kind of network methods where we looked at correlations, but these are kind of classical correlations between observables. And it's not really clear what is quantum in there a priori. And so the question would be whether we can use this kind of framework, this kind of machinery now to really extract signatures of quantum entanglement, of non-Gaussian quantum entanglement in these systems. And then finally, kind of the more long-term question is like, can we use these non-Gaussian operations to implement interesting quantum information protocols to achieve a quantum advantage? We also have a big parameter estimation and metrology activity in our group. So we are also very interested in understanding how these non-Gaussian effects can play a role there. And so this is kind of the outline for what we will be working on the following years, at least on the theory side. So what remains is to thank my collaborators. So for the steering part of this work, and specifically for the monogamy, we had a very nice collaboration with the group of Chongyi He in Beijing. And so particularly Yu Xiang was the postdoc who did a lot of work on this monogamy. There is also Shuhang Liu, who also did a lot of work. Sadly, he wasn't at the Great Wall when we went there together, so I don't have a picture of him. But so I also want to give a shout out to him for all the hard work. Then there is also the machine learning part, which was done in collaboration with people from Rome, with a group of Marco Barbieri. And so we were specifically very lucky to have Valeria Cimini on the picture here join us for a few months in Paris right before the COVID pandemic hit to basically develop this whole machine learning neural network formalism to detect Wigner negativity. So this was a very fruitful collaboration as well. And then last but not least, there is our group that I want to thank. So here, I told you before that we are still kind of in semi-lockdown. So the other permanent people here are Nicolas and Valentina. So this picture was taken very recently, which is why they all have masks. Most of the theorists, except for Ilya here, are not on the picture because they are mainly working from home. But here you see, most of us are actually doing experiments, which is why they still go to the lab and why they still can go outside to take a group picture together, at least with some of the group. And so the other theoreticians are Ilya, who is sitting here, and Giacomo, who is at the moment living in Germany and working from home. They are both of them working really on parameter estimation. So this is the rest of the theory group, let's say, and all the others are really doing experiments on all the kind of stuff that I discussed. All of us kind of work a little bit between experiment and theory, but like experimentalists, once you like turn on their laser, you cannot really convince them to keep on doing calculations. So it's kind of clear that this is really the thing they love. And so then finally, I want to kind of give you a quick propaganda slide, like the bibliography. So these are basically all the papers that contain things that I mentioned in my talk. And I want to highlight maybe finally, and very recently I wrote this tutorial on non-Gaussian states, how you describe them on phase space, specifically focusing on multimode continuous variable systems. So if you want to learn about the technical details and about basically how to really attack these systems, how to do the theory and so on, this work more or less is kind of tries to be a pedagogical introduction to more or less everything that I know about this subject and kind of the important results that kind of shape the field and so on. So if you're interested, please have a look. Tell me what you think about it. If you have questions, don't hesitate to drop me an email. If you find errors, this would also be very nice that you tell me. So yeah, I think with this, I want to conclude my talk, and I thank you very much for the attention. I'm sorry that my PowerPoint somehow crashed. No idea why this happened. But so yeah, and of course, very happy to hear your questions.
Thank you very much, Mattia. That was a really cool talk. It's clearer than I expected, actually. Okay, do we have any questions?
Okay, I have a very general question. So, of course, the last point that you mentioned in your outlook is that you would like to find some advantages or something and so on. Which relates to maybe the first question that I would have is, you mentioned that indeed to have Wigner negativity is a necessary condition for some quantum advantage to happen. But are there concrete examples where you can say sufficient condition, like if we have something like that or that type of structure, then we actually can do this?
Honestly, to me, this is one of my big, I would say, frustrations on the one hand, but on the other hand, it's also a nice opportunity for future work, I guess. But so there are kind of clear requirements, like you need entanglement in some way. Usually in these setups, you need Wigner negativity, which you can formally show. But to really say like this is a set of ingredients, like these are the sufficient criteria that you need to do something interesting, I don't know of any kind of closed result on this. So of course you could take, let's say, the top-down approach, saying, well, we have, for example, Gaussian boson sampling, which is a setup where you have, let's say, you start with a big Gaussian state, and then you apply these photon number resolving detectors on it, which is basically, you could say, well, you are with part of your detectors maybe doing some kind of big generalized photon subtraction, something like this, and then you get a complicated state that is maybe hard to simulate. So you could take this setup, dissect it, and look at all its elements, and clearly, well, we know that there should be a quantum advantage there. But to me, it still is the frustrating thing there. Then would be that, well, all you do at the end is counting photons. And so I wouldn't say that this is really like a completely continuous variable protocol. So I think that there is definitely still something that is missing. I mean, the same thing you could say, we take all the ingredients that we know that we need to do universal quantum computing with continuous variables, like GKP states or whatever kind of states you use to encode your qubits and so on. This global thing, I mean, framework clearly has all the ingredients that allows you to get a quantum advantage, but it probably has way too much. And so to me, like the minimal setup that you need to get a quantum advantage, and kind of the physical intuition that goes with it, is still something that is kind of missing. I like to make the kind of the comparison to when you look at what people do in what we call in optics discrete variables. When you look at a normal boson sampling setup, you have photons going in, you detect your photons at the end, and what you are looking at from a physics point of view is interference between the different bosons, right? Between the different photons. And so this gives you like the idea that this many particle or many photon interference, this generalization of the Hongo-Mandel effect, is kind of the physical phenomenon that gives you this kind of quantum hardness in boson sampling. And for continuous variables, there isn't some kind of general idea like this. And I find this quite frustrating. And this is actually one of the things that I would like to find. So I have a kind of a conjecture that probably this kind of non-Gaussian entanglement that you could get might play an important role in this getting a quantum advantage with these systems, but this remains to be shown, I think. So
thank you.
Okay, any other questions?
Well, I have another one since I'm an expert there. I would, some years ago, I haven't followed this literature very closely, but some years ago there was, I think he's associated with the name of Nicolas Menicucci, who came up with something like cluster states with continuous variables or something of that type. And I think that this company Xanadu in Canada is trying to implement that thing. Do you know anything about these? Is it closely related to what you're doing? Is there any difference?
So, so of course, I mean, especially the people of Xanadu, we discuss, let's say, semi-regularly with them on different ideas and so on. So to me, we have kind of complementary approaches in the sense. Also, when you look at the work of Nick Menicucci, what they are really doing is they are trying to build like a kind of a measurement-based universal fault-tolerant quantum computer, where these cluster states, they play a very important role because they are kind of the backbone that you will use for your measurement-based protocols. Then you also need, basically, you need to have this fault tolerance come in somewhere. And this is, from an optics point of view, the really difficult part. You need to create these ridiculously highly non-Gaussian states, which you can use either cat states, but most people like to use these kind of grid states, these what you call GKP states, which have basically ideally a Wigner function, which are kind of localized delta peaks in your phase space. And so this is ridiculously hard to make in optics. But like Xanadu, for example, they have this whole idea of they want to use Gaussian boson sampling or a kind of Gaussian boson sampling setup to post-select on certain outcomes in their boson sampler to then get one of these GKP states out in another mode. And so this is, of course, very difficult. So they want to like do a lot of multiplexing to increase the probability of at least here or there obtaining one. So, and then with these GKP states, you can create something which is effectively acting like a qubit. You can connect this to your big Gaussian cluster state, and then you can start doing measurements on it and basically ultimately obtain, translate everything back to a framework of, let's say, more standard qubit-based quantum computing, do error correction and so on. So this is the kind of general scheme that Xanadu is working on. This is a scheme also that that Nick Menicucci and so on is theoretically developing. We take a bit of a different perspective in the sense, well, anyway, like Xanadu, they are a company which has, I think, 50 employees or more. They have hundreds of millions of euros. They have, we are discussing on whether we should buy a photon number resolving detector. They have a fridge which has hundreds of them in it. So I mean, as a research group, you cannot compete with this kind of growing company. So our approach is more to try and do more the physics side of the story, try to understand the physics of what is going on in these systems, to try to basically also look at alternative approaches, like basically let go of this idea of wanting to do universal quantum computing and more try to find, let's say, okay, can't we find some kind of interesting system to simulate with these networks, or can't we use this kind of network approach to solve an interesting like graph theory related problem, this kind of things, without needing actually to have all the machinery for universal fault tolerant quantum computing. So this is kind of our long-term perspective, the kind of road that we try to follow for ourselves, to not really compete but more complement these other big players, let's say.
Thank you.
Okay, I have actually a couple of questions about the the slides that we have seen today.
Mhm.
The first one about the Wigner negativity. You mentioned that there is some kind of relation between the Wigner negativity condition and the Fission information matrix.
Yes, let me.
How is this relation?
So this was here, right? Okay, so this is a. So this basically stems from the observation when I wrote down this condition at some point and showed it to one of the people working with us on the metrology. He said, well, I mean, your condition basically this inverse of the covariance matrix. This is basically the Fisher information matrix for a Gaussian state. So he said it's kind of interesting that you find a condition that is related not to the covariance matrix, but to the inverse of it. So then, of course, this is kind of you take this inverse, you have to project it to B. So this would be kind of related to asking the question, okay, when I do measurements on this kind of global state, what's the metrological information, let's say, that is in this mode B in which I subtract the photon, and then this condition on the trace basically says that you should have some small quantum advantage. But so, as I said, to me, it's not clear whether this is just a coincidence or whether this is because ultimately with the Gaussian states, having a quantum advantage in metrology basically boils down to having squeezing in the right mode. So you could also say, well, this is just a condition to say in the mode where you're subtracting the photon, you should have a sufficient amount of squeezing somehow. And yeah, so in this sense, to me, it's not really clear whether there is a more fundamental relation to the Fisher information. At some point, we try to see whether we could derive something that if you take a more general quantum state and you subtract photons from it, whether you could still find maybe that the negativity would be related somehow, or that the Wigner function that you get would be related to the Fisher information of this more general quantum state. But we never managed to really get anywhere in this way. So it's a small observation, but it might be an observation that's just related to the fact that, well, I mean, Gaussian states in general, well, you have squeezing and you have mode chain and beam splitters, and that's basically it. So I mean,
that's true. Makes sense. Oh, thanks.
Mm.
Also, I have a question about the graphs you showed for the accuracy of the neural network.
Yes.
They all go up to 95. Is it possible? Is 95 some kind of upper bound, or we just didn't want to go higher?
So from everything we tried, of course, this is the disadvantage of using machine learning algorithms. Well, I mean, usually you kind of close your eyes and you go and you try to get it as good as possible. So I have no idea whether there is like a formal upper bound somewhere. This is just the best kind of results that we got out. And so, as I said, we are kind of working on tweaking the algorithm a little bit to improve it, because I mean, there's a lot of things under the hood that I didn't really discuss, because so I showed you here, this is what kind of the data would look like. So there are then many things that you do, because just kind of inserting this kind of trace into an algorithm, it's annoying. So what we do is we turn this into a histogram. We group, so this on the axis here, you have the phase of your homodyne detectors. So you basically are scanning kind of X quadrature, P quadrature, and like everything between it, right? And so then you have measurement outcomes for every phase. And we group these phases in slices, and we group all of these. So let's say you have bin here, a bin here, a bin here. You group all of these data together, and then we also make a histogram of quadratures here. And so actually what we found is that when you have 3 modes, you can make this extremely rough. Like you only need like 5 bins or 10 bins in the, let's say, in the measurement direction, and you need 3 or 4 phases, and you basically have enough information to make it work. Of course, you need to then do this for every mode, right? And if you go to more modes, you actually have to refine this information. This was basically why we had a problem here with these plots. But so, I mean, to me, it's clear that there is, when we do this pre-treatment of the data that we inject into this algorithm, there is a lot of information that we throw out. Like, even if we assume that we have correlated measurements, so where you take into account correlations between the different quadratures when you sample, like we throw out these correlations, we don't use them. So there has to be more to be gained in there. And I guess this would allow us in principle to push this barrier up. But the problem is that then these algorithms become so heavy that I mean, if you have to do something which is almost like a tomography again, you kind of lose the advantage of having such an algorithm. So this is kind of what we are now looking at. And to me, it's still remarkable that we don't need these correlations. Like, I'm quite sure at some point, we actually try to even by hand put in many data where we thought like, here, you definitely have to somehow look at the correlation. And even then the thing kept on working. So it's clear that there is some effect of this photon subtraction that this algorithm just sees. And then it says, well, if I see this, there has to be a photon subtraction. And well, clearly, I mean, the rest of the noise is such that this can only be explained by negativity. So, but then if you would so to me, this is a very good way, if you know what you have on your optical table, and you know that you are not getting like super exotic non-Gaussian states in there from time to time, it's a good way to check kind of what your state that you have at the end is behaving like. If you say like, I have no idea what state I have here, and I want to check whether it has negativity, this is probably not the best method because it's very biased by the training data that you use. And the training data rely on the fact that we can simulate them. And so of course we cannot simulate anything where you would have a quantum advantage, let's say, for example, like if I have something which is too complicated to simulate, well, I mean, this approach will not work anymore. So, which is now why we are trying to see what happens when we kind of feed in data of states that the algorithm has not been trained for, like whether it actually kind of can make sense of these states or not. And well, I guess as long as the states resemble more or less the type of states, I mean, it works surprisingly well, but I'm sure that there will be a barrier where all of a sudden things start to go horribly wrong. So
yeah, true. One last question, if I may. In the slide beyond tomography, there was some graphs with some lines describing the correlations beyond tomography.
Beyond, yeah. Yes.
Okay, so these lines, they correspond to some bipartite correlations or multipartite correlations? Or?
So the correlations here, so every line just connects two vertices, so 2 optical modes. And this would be just when you look at, so these are photon number correlations. So you look at the number, let's say that we take, I don't know, maybe let's take one of the lines here between these 2. This would tell us how strongly the number of photons in this mode is correlated to the number of photons in this mode. So it just visualizes this bipartite correlation. And so this is kind of an approach that says, like a full tomography of the system is completely undoable. Like tomography scales exponentially if you have in the number of modes, because you have to kind of cycle all the phases for like all the different combinations. But if you just have 2 modes, this is doable. And then the idea is, well, what we could do is we could look at not just at every single mode, but we could also look at all the possible pairs of modes in our system, get the reduced state Wigner function for these pairs of modes, and try to extract some information from that. And because we have all of them for all the pairs of modes, maybe there is some additional information in there. And so this is kind of a first step to just see, well, okay, when we look at, so the reason we took photon number correlations is basically because this is, it's a non-Gaussian correlation. It's of fourth order in the quadrature. So in principle, it should be more sensitive to kind of non-Gaussian effects and so on. But basically, this is just the naive approach. It's a completely numerical work. It's kind of the best thing that we could squeeze out, and so it's a first step to see that indeed, well, we can see things happening in these systems on the level of correlations when we subtract photons.
Okay, so there was no study of, for instance, multipartite correlations.
There was no study of multipartite correlations. There was no study of, let's say, really quantum correlations or anything. So there is definitely space to kind of extend, let's say.
Okay, and when you subtract up to 10 photons, the subtraction always okay. In the graph, we have many dots. Every dot is a supernode.
Sorry, may I just interrupt for a moment? I mean, I don't know to which extent, I know that some people may be ashamed of leaving the meeting. So if this becomes a more technical discussion,
yeah, sure.
We may just thank the speaker and give a closing to the session. Of course, the people who want to stay online longer and follow a more technical discussion can also do that. Yes. But I would just encourage those who, since the discussion, unless there is a question from any other of the audience, I would suggest that we can close the official session here.